evening. How are you doing? Good.
Okay, so let us get started. So thanks for coming. Today is the big day for Chamila, and he has been with us. You coming in
2011.
11? So it's pretty fast, right? And so he has been working on this PhD dissertation on the cement materials and completed the research work. And today he's going to present it as a public defense for his degree. And he actually worked a lot more topics in addition to the cements. So will you please sort of present it in about 45 minutes, and then we will open for the question for the committee members first, and then the general audience. So you can start.
Thank you, Dr. Ching, and good evening, ladies and gentlemen. My PhD dissertation topic is structure and mechanical properties of cement and intimately compound ab initio simulation methods. So let me give you a quick overview. The major part of my thesis is on cement minerals and cement modeling via theoretical methods. And a smaller part is on developing ab initio molecular dynamics method, taking intermittently compounds as examples. Or as an example, and preferably finding some applicability towards simulating cement compounds. So the outline of cement modeling is as follows. So what we hope to achieve in this study is to understand the basics by simulating known crystalline structures of cement mineral, and hopefully at the end of the day try to find a model for cement. For this, we started off with 4 CSH crystals, calcium silicate hydrate crystals, and we looked at electronic structure, mechanical property, developed some quantum mechanical metrics to characterize these crystals, and preferably find some correlations between these two. Since 4 is not enough, obviously, we expanded it to a 20 crystal database for CSH. And these are published in these papers. And finally, in an attempt to understand the cement material as a whole, there was a recent review by Richardson that showed that made some models for CSH one type of material, which I will explain a little bit later. And we studied those models, and we applied our quantum mechanical metric to them to validate and hopefully expand it to CaSH, which is calcium aluminosilicate hydrate, which is the main impurity of CSH. On the second part is developing ab initio molecular dynamics methods. We developed 2 types of methods. First, an attempt to simulate mechanical properties at high temperature. And second is using ab initio molecular dynamics to simulate alloy. Both of which are major objectives for cement, but at this time we're not experienced enough to apply this to cement compounds. So we used T1 and T2 phases of molybdenum silicon boron system as an example. So let me give you a little bit of motivation why we need to do simulations in cement. Obviously, cement is the most used construction material in the world, about 3 billion tons annually. And it's been used since the Romans to now. And it has a wide range of applications like radioactive waste storage, biological application, and that is cement. And CSH, calcium silicate hydrate, is the main binding phase of cement, and assumed to be responsible for the mechanical properties of cement. And the other side of the coin, of course, is it also contributes 5–10% to the carbon dioxide emissions in the world. And it is responsible for soil erosion because it's used so much. but heat island effect, concrete dust related with the health hazards and all that. To understand both positives and negatives of this material, we have to understand it at a fundamental level, atomistic level. So this study is an attempt to do that. This picture gives you the structural complexity of cement, starting from the cement paste what you find in the walls. And at each level, at each length scale, you can see that the CSH matrix is made up of well, different structural, as far as we can tell, different structural arrangements. And it is a porous material inherently, and porosity has an inherent role to play in this. As far as simulation goes, we are basically focusing on these two levels at nanoscale to find an atomistic model for cement. Before we go further, let me introduce to the cement chemist notation. C is calcium oxide, S is silicon dioxide, and H represent both structural water and hydroxyl. And COS ratio, I'll call time and again, is a very important characterization metric in cement research. These dashes is to represent the inhomogeneity of cement. It represents both crystalline, amorphous, non-stoichiometric forms of calcium silicate hydrates. So this is first and foremost a modeling study. So let me briefly review some of the descriptive models that's been going on. Not to bore the audience with having to read this, but just to give a time scale of what these models started from. It started as far as 1946 by Powers and Brownyard, which they described the structure of cement by capillary porosity, and it's a colloidal model. And all the way the models changed over the years, and finally one is more somewhat accepted model by Jennings, which is called Jennings CM2 model, which describes cement sort of qualitatively. So he introduced this 4 nanometer cement particle, and he says that the diversity in mechanical properties comes from arrangement of the cement particle in space, having large porosity and smaller gel porosity, and also within the cement particle itself you have interglobular porosity. And also, because this is researched so many years, there are some mistakes made over the years. For example, in this study where in Jennings CM1 model, they made a mistake in right wall refinement, which gave them a wrong density. And all the models based on that density became wrong as well. So making a model, you had to keep those things in mind. Now, let's look at some of the predictive models. Predictive models are atomistic models, usually mainly based on molecular dynamics and molecular mechanics, and also Monte Carlo techniques. And these are relatively new field because of the advancement of computation is relatively new. And let me just say a few words about the final model from Delano, which he had about a 60,000 atom molecular dynamics calculation, trying to mimic the COS ratio, the average COS ratio of known cement, to understand the porosity. And this also does not give the entire picture, or is not very consistent, not consistent with the whole, all the observations, experimental observations over the years. Let me tell you a little bit about the computational methods we use. We use 2 basic packages: Vienna ab initio simulation package and linear orthogonalized linear combination of atomic orbitals, which was built and maintained by Professor Cheng and Professor Rulis. Both these packages use density functional theory, and the VASP uses a plane wave basis set. Within we used PB potential mostly, PB approximation. And VASP is very efficient in optimizing geometry of solids and calculating force and stress tensors. Oil CEO uses an atomic orbital basis set, because of which it is very efficient in calculating electronic structure very efficiently on large and complex systems. An elastic property calculation, we use an approach called stress strain analysis approach by solving the tensorial form of Hooke's law to calculate the CIJ. We use vast package to do this. Once we get the CIJ tensor, we can calculate the bulk mechanical properties like bulk modulus and shear modulus from Bigger-Cruz-Hill approximation. Let me tell a little bit about the electronic structure calculation. Our electronic structure calculation is mainly focused on bond order, which is calculated within the Mulliken-Euler population scheme. And bond order you can roughly think of as the strength of the bonds, the strength of pair of atoms. So we'll define it as the strength of the bond. And this is important to understand the structure. Inherently, the structure depends on its bonds. So it is a nice value to know, or not a value, it's a nice data to know and to understand the structure. And in this study, because of the complexity and the diversity of the amount of crystals we use, we introduced the concept of total bond order density, which is a single parameter. It simply is the cumulative bond order of all pairs of atoms in the simulation cell divided by cell volume to normalize it. And we hope that the total bond order density gives a description of the cohesion of a given crystal. So it will be easier to compare if we have a wide variety of crystals. And if the total bond order density is not enough, well, we introduce the partial bond order density to further analyze the material we are discussing today. So partial bond order density is the cumulative bond order of each species of bond in the crystal. For example, let's say calcium oxide bond, we'll add these bond orders up and divide by cell volume to calculate the partial bond order density. So, as I said before, we start off with 4 popular crystals. These are popular because they are the first and, they are the most used as the basis to build atomistic models, as I showed earlier. We use genite, double morite 9A, 11A, and 14A crystals. These crystals have infinitely long chains, silicate chains, and in between this you have calcium atoms. So let's call this as a layer. So these are layered compounds. All these 4 crystals are layered compounds. And between these layers you have structural water and hydroxyl and perhaps calcium ions, and it varies considerably. This is what actually giving the complexity of the cement. And so we started off with these 4 compounds, and you can see in the table you see the percent different from the structural optimization. It's still within a reasonable limit. And also, one thing to keep in mind is that XRD never gives the positions of hydrogens. So when you're doing a simulation, the hydrogen has to be added, and which is one of the reasons the structural optimization is important. These band structures of the 4 compounds in the previous slide shows the importance of structural optimization. It's the before band structure and after band structure of the structural optimization shows that before you get a lot of unrealistic gap states that shows you your cell is not optimized. And after relaxation, of course, the gap cleans up and you get a clear band gap showing these are all the insulators as it should be. Now let's focus on the electronic structure and bonding of these 4 crystals. So here you have a scatter plot of bond order versus bond length. This plot makes it easier to identify what types of bond you have and what strength and distribution of the bonds. As one may expect, you have 4 main types of bonds: silicon oxide bond, calcium oxide, covalent OH bond from water or either hydroxyl, and also this is the hydrogen bond. And one can see the dispersion or the broadness of the hydrogen bond length and bond order-wise. And one thing that should get your attention immediately is the strength of these, the highest, strongest hydrogen bonds. These hydrogen bonds is about half of the covalent bond strength. And for material like biosystems, where hydrogen bonds play a major role, they have their hydrogen bonds is about 1/10 or 100, and they still play a major role. That's why we thought, well, CSH, the hydrogen bond, may play a major role as well. So we studied it even further. At first, we divided the hydrogen bonds just to make the analysis easier between the hydrogen bonds between water molecules and the rest of the hydrogen bonds. But with these 4 crystals, we couldn't find any definitive arguments against which of these types of hydrogen bonds are stronger or important for the structure. But you can generally see that hydrogen bonds between water, shown in pink here, is less than the other hydrogen bonds. So to test our metric, our hypothesis of how effective is bond order density, and to find the relation between that and the mechanical properties of the cement crystals, we made this plot. And you can see at first glance the trend of the mechanical properties seems to correlate fairly, well, I wouldn't say well, but it seems to correlate somehow with bond order density, as opposed to the traditional COS ratio, which gives inverse trend. And also the experimental study done by O is close to our value, just to make it consistent. And experimentally measuring mechanical properties in cement crystals is extremely difficult, just because of the difficulty of synthesizing cement crystals. Now, then, after the 4 crystals, we expanded the database to 20 CSH crystals to test these hypotheses or metrics we had. So we selected 20 crystals from a review. And because we're using 20 crystals, now we had to classify them to make the analysis easier. We grouped the clinker phases and hydroxide phases in group A, but the rest we grouped according to modified Strunz classification. Why we needed to do this was the standing classification made by Taylor 40-something years ago was not adequate, or did not show enough of the structural complexity of cement. And modified Strunz classification is based on the silicate polymerization indicated by Qn, where N being the number of shared oxygen atoms between silicate tetrahedra. For example, in this picture you have 3 or 4 silicate tetrahedra, and the silicate tetrahedra in the middle share 3 oxygen atoms. So this tetrahedra is defined as Q3. So in same logic, the group B crystals is defined Q0, which has no shared oxygen, so it's silicate monomers. And group C, the sorosilicates, is Q1, which have one shared oxygen, which gives rise to silicate dimers. And group D, inosilicates, has 2 shared oxygen, which gives rise, if you have 2 shared electrons, the chain is infinitely extendable. So that's the classification of the crystals that we use. So this is the 20 crystals that we used for this study, part of the study. You have group A, clinker and hydroxides, and the group B, starting from opalite, has monomeric silicates, and group C has dimeric silicates. Sometimes you have trimeric and monomeric averaging into Q1. And group D crystals have infinitely long silicate chains, giving rise to layered structures and interlayer complexities with the structure of water and calcium, so on and so forth. So to put these 20 crystals in perspective, would it make sense to use 20 crystal? Would it tell anything about cement at all? We compared it with these two experimental studies done for synthetic cement, not crystal, synthetic cement, where they try to find a correlation between water to silicon ratio against COS ratio, and they found this trend. So we thought we should put our crystal in the same diagram to see if there's any correlation. And indeed, some of our crystals, especially the D group crystals, have a close relation with the experimental findings, and which gives you the promise that, okay, maybe these crystals will tell something about real cement at the end of the day. But you can see there's a separate trend here, so we looked at those crystals closely, and we found that these crystals have only hydroxyl groups in the interlayer or within the crystal structure, and no water, which makes sense that the real cement one can assume to have both structural water and hydroxyl together. So, and going from that, this is the bond order versus bond length plots for selected crystals from each group. From the clinker phase, halite is the main clinker, and from group B we took opalite, and then group C solnite, and group D genite. And as before, as the four plots before, we see the same type of bonding, but we can see differences between each group. You can see that the group D has a wide range of hydrogen bonding. But group B and group C have a narrow band, both bond length and bond order. Maybe more bond length than bond order. So there's some structural, some chemical differences between these groups. And also, group B and C have much more stronger hydrogen bonds than group D. This is probably because all D group elements are crystals are layered structures, and you can have different amounts of structural water within the interlayer, giving rise to a wide range of hydrogen bonds. And in this case, we compared the hydrogen bonds between the water and water and other hydrogen bonds, and we found that almost consistently the hydrogen bonds between water is smaller than the rest. And also another thing that we saw was that, see, this silicon oxygen bond length is very narrow, if you can see that. But bond order is much broader. And all the studies that analyzes this thinks that silicates are very homogeneous. In fact, they're not. They may be structural-wise, but they're not strength-wise. And how this come into play is when you're trying to analyze a vibrational spectrum, because then the bond strength comes into play. And you can see, if you look closely enough, this is not just a broad band. There's some gap here. So we looked at this very closely, and we found out that silicates that is connected to hydroxyl has a lower bond order than the other ones. So this should be important information when you're trying to analyze spectroscopic data, for example. Moving on, we plotted, we think, the total bond order density as a metric, and so we plotted it against the traditional COS ratio to find out any similarities. Well, the first thing you see is total bond order density is obviously much more sensitive because it's sensitive to the chemistry of the crystal. And for the same COS ratio, you got a vastly different total bond order density. But in general, the TBOD and COS ratio has an inverse relationship, which makes sense because when you increase COS ratio, you have more calcium ions making more calcium oxide bonds. These are weaker bonds, reducing the TBOD. And from first glance, we divided TBOD into three groups, high TBOD, medium, and low. And we found out that most of the D group crystals that are supposedly will represent cement belongs to the medium TBOD group. So if you want to pick crystals as a seed models to make a structure, that's what I would go with. And although all the crystals as a whole doesn't make much relationship, if you take this take each trans group separately, you can see that group B has a linear relationship with COS ratio, and group C has an exponential relationship with COS ratio, but group D is much scattered. Although you can say the COS ratio in group D is very small, but you have large distribution in terms of TBOD. So to understand this further, we made this ternary plot for the composition of calcium, silicon, and hydrogen to understand, to identify if there's any preferred TBOD regions, because any cement you find has to fall within this triangle. So we wanted to find out, is there any preferred total bond order density regions that we can somehow engineer the chemistry, the composition to obtain. And indeed we do. We have the anhydrous or the CS crystals have the lowest TBOD. Also the hydroxide phases. Then the crystals with hydroxyl only have medium TBOD, and there's a region here that has the highest TBOD. And the crystal Suolnite is a special case, which we'll go into detail later, that has the highest TBOD. So then we'll look at the mechanical property, make the same ternary diagram to find out where the mechanical properties, how the mechanical properties change with the composition of CSH crystals. And we find some relations. So the mechanical property is shear modulus, bulk modulus, and Young's modulus we check. We find that the highest mechanical property is from anhydrous phases, CSH phases. That is phases without any water or hydroxyl in it. And intermediate mechanical properties can be found for CSH crystals with only hydroxyl. And if you increase the hydration, the crystals with both structural or then hydroxyl has the least mechanical properties. Then we figured we should find the relationship between HOS ratio as well. Why? You have CSH three things. So you can have COS ratio, HOS ratio, or SOC ratio. SOC ratio didn't give us anything, but we found that COS ratio actually is a very poor characterization metric in terms of mechanical properties. There's no correlation whatsoever. But HOS ratio has an inverse correlation, at least within the sample we considered, with the mechanical properties. And also there's only 3 bulk mechanical properties. We found that Poisson's ratio actually is not correlated anything, any molar ratio. Then we tested our TBOD metric against mechanical properties, and unfortunately we found that TBOD by itself do not correlate at all with the bulk mechanical properties. So we went further and analyzed the partial bond order density, PBOD, for each species, silicon oxide, calcium oxide, and hydrogen bonding. And you can see that going against the norm, silicon oxide bond order density gives the least correlation with the mechanical property. It is widely accepted that silicates will govern the mechanics of mechanical properties of cement, but that does not seems to be the case if you consider the electronic structure. Calcium oxide, on the other hand, shows much better correlation, well, relatively speaking. But interestingly, hydrogen bond order density gives at least relatively best correlation. When you increase the hydrogen bond order density, the mechanical properties goes down, but surprisingly, at some instances, it goes up again. The only deciding factor is hydrogen bond. So that was not known before. So to test the idea, is it just because of hydrogen bond order density? Is it just electronic structure or just number of water molecules? We plotted percentage water and percentage hydroxyl in these crystals, and we found out they don't make much correlation. So it is indeed the strength of the bonds and the number of bonds that decide. correlate with the mechanical properties. So, since hydrogen bonds is so important, we decided to find out how many types of hydrogen bonds are there in CSH. If you consider CSH, there's only 4 types. Hydrogen bond has two atoms, oxygen and hydrogen. So there's 4 environments I can find oxygen in: tetrahedra with hydroxyl, water, and calcium hydroxide. And 3 of them have hydrogens. So if you find the combinations, you got 12 combinations of 12 types of hydrogen bonds. That's all there could be. And at first glance, there's no preferable hydrogen bonds that you can logically say this is the best and this is the worst. For me, they all seems equally plausible. So we tested that by analyzing the bond orders of all crystals. And we found out that in fact that's not true. There are preferential cases. That these 4 cases are non-existent, at least within the database we searched. And the most important, it seems, at least the most frequent, are these 3 cases, where T and TH, T and water, and water and water. And again, water and water comes to be the smallest percentage of hydrogen bonds in the CSH crystals. So we made the same ternary plot to find out is there any preferential composition for hydrogen bond order density, and indeed we come to the same crystal, same composition which the Sewellite crystal is. So it seems that Sewellite crystal have very important hydrogen bonding network, which we'll go into right now. So going back to the Sewellite bond order versus bond length scatter plot, we found that the highest bond order values are from TTH bonds, and relatively lower ones are TW ones. And you can't see a distribution here. It's not that you have 2 hydrogen bonds. You have many hydrogen bonds, except these are all the same, which is, although we did quite a lot of relaxation, the crystal seems to be in perfect harmonious state in terms of hydrogen bonds. And for the total, if you look at the total density of state, the main contribution to the valence band is from hydroxyl and hydrogen bonds, which gives rise to it this unique property. So let's look at the crystal structure. It's arranged in a very peculiar way. You have silicate dimers arranged in a perpendicular fashion, and each silicate dimer has a hydroxyl and a water molecule connected via hydrogen bonds, and the entire network is based on the hydrogen bonding connections, these strong hydrogen bonding connections, which gives its higher mechanical properties. So these crystals should be further studied in future, hopefully. So let's go to the Richardson models. As I said, CSH1 type of cement. So let me introduce what CSH1 means. All synthetic CSH can be classified into 2 categories. One that have high XRD patterns, one that have poor XRD patterns. And the higher XRD patterns grouped into CSH1 and CSH2. CSH1 have lower COS ratio and CSH2 have higher COS ratio. And CSH1 is assumed to be coming based on tobomorite family of crystals, the 4 crystals we used in the first study. And Richardson used these family of crystals as a template and made models such that it's consistent with experimental observation. And CSH2 comes from Genite family of crystals. Well, Genite is 1 crystal. So how he made these models in his review came out last year is that he considered all the experimental observations up to date for CSH1 type of cement. And then he carefully analyzed the crystal chemical principles from the known 35 crystalline minerals. And he optimized the atomic positions as well as crystalline parameters to come up with a database of 16 models as a starter. And with our quantum mechanical metrics, which we based on 20 crystals, maybe perhaps we could extend it further maybe in the future, But we can do the same kind of analysis to maybe validate and understand this, the CSH1 models proposed by Richardson. And also, we can extend the CSH1 to CASH1 to make a more comprehensive list of models for cement or CSH1 type of cement. So from that 16 crystal database, I took 2 crystals. These are all infinite long silicate chain crystals. So these are, both of these crystals are layered as a starting. This study, of course, is still at an early stage. And why I choose these 2 crystals is that one has calcium in the interlayer, the other one has no calcium in the interlayer. And of course, the infinitely long silicate chains had to be taken out because we were thinking to extend this to calcium aluminum silicates. And it is known that the aluminum replacement for silicon can only be done for bridging tetrahedron. So you have three silicate tetrahedral chain here, and this is called a bridging tetrahedra in the middle. And aluminum is always replaced for the bridging tetrahedron. And also there's a preferred percentage of, or maximum percentage of aluminum replacement, which I'm not going to go into detail. So from that, we made this 3 calcium aluminosilicate models. And of course, when you replace 4-weight and silicon with 5-weight and aluminium, you have to carefully balance the charge. To do that, you have to either add calcium atoms for every 2 aluminium replacement, or add 2 hydrogen atoms to balance the charge. So in this case, there were enough room to put hydrogen, so I made 2 models. But in this case, it was all saturated. There's no room to put any hydroxyl in the interlayer, so we have to settle with just 1 calcium atom to balance the charge. Now, the electronic structure was calculated for these 5 models, and the bond order versus bond length plots show a typical behavior as we seen for the D group crystals shown before. But there are a few things to take home. That, for example, we didn't do any CASH crystals. You can see that the aluminum oxide bonds is as strong as silicon oxide bonds. And also, the model derived from this one, this structure has higher hydrogen bonding or richer hydrogen bonding network compared to the other one. So that means the silicon, calcium atoms in the interlayer somehow enhances the hydrogen bonding network of the crystal, which could be an important factor when you study the crystals. And also, the highest total bond order density is this crystal, and the lowest one is this. So, cohesion-wise, the calcium atoms in the interlayer seems to play a significant role in CASH crystals. All right, now to summarize these 4 studies, we introduced a TBOD metric that seems to be better than the traditional COS ratio. We did extensive bond order analysis that would be very helpful in interpreting spectroscopic data in the future, and we found out some unique crystals that have a unique hydrogen bonding network. We showed some mechanical property relations, and we found that partial bond order density of hydrogen bonds and calcium oxide and also HOS ratio correlate well with the mechanical properties. We proposed 12 types of hydrogen bonds and found the most significant 3 out of those 12. Then we use our quantum mechanical derived metrics to test and validate Richardson models and extend that to calcium aluminosilicate models. Okay, so shift gears a little bit. Let's go to ab initio molecular dynamics studies of intermetallic compounds. As I said, I did 2 types of ab initio molecular dynamics methods. As I said, I picked intimately compounds to do these tests. And why I picked molybdenum silicon boron system is as follows. MOSIB is believed to be a good candidate for high temperature structural materials. It has high melting point, very good mechanical properties at higher temperature, around 2000 Celsius, and it has good mechanical properties at room temperature too. And why we need a new one? Because the current nickel-based super alloys is not good enough. This is good enough up to 1600 Celsius, but beyond that, it's not. It breaks down. So because of that, we have to study this molybdenum silicon boron system. So we studied T1 and T2 phases of this compound and alloys of this. This is, if this works, I mean, if it is a good candidate, it would be useful in aerospace, power generation, and any high temperature structural application. So, why we needed a theoretical technique to assess high temperature material is one, theoretical simulation is easily done, and it's very difficult to do this in experiment. And the theoretical techniques existing techniques that uses ground state calculation and try to extrapolate the mechanical properties to high temperature, which I will show later, does not work after a certain temperature. It fails. So what we did was we used ab initio molecular dynamics to obtain high temperature structures. Then using those structures, we used stress strain method to calculate the elastic and mechanical properties. So to give you a brief introduction about the two crystalline phases, T1 and T2 phases have D8M and D8L crystal structure with AB. It's a stacking crystal structure with molybdenum silicon elements. So I'm not going to talk about the details of the method, but just to give results. This is a comparison of our calculated value against the experimentally found results given by this red dots. For T1 phase, we could only find for room temperature measurements, which is close to our results. But for T2 phase, there was a study done for up to 1500 Celsius, and the CIJ values relate closely to the experimentally found values. And also the same case with the average or bulk mechanical properties, bulk modulus, shear modulus, Young's modulus, and Poisson ratio. The T1 phase agrees well at room temperature with the experiment, and T2 phase agrees well with the experiment as well. And as I said before, the techniques used before by calculating a ground state structure and extrapolating with maybe a fit to the equation of state is good up to a certain temperature, but then it starts to fail. And we proved that a direct method is much more suitable and much more effective and accurate to do this kind of simulations. Then we used ab initio MD for alloying. And we needed a problem to use this method. So what we found was T1 phase have one drawback. T1 phase molybdenum silicon crystal is anisotropic mechanically. So the expansion in C direction is different from expansion in A direction. It is detrimental to structural elements because it induces cracking when expanded. So a popular method to reduce this anisotropy of thermal expansion is by alloy. So we use two cases. We replace molybdenum with vanadium at first. Then we replace silicon with aluminium. And both these cases have good reasons to do it. For example, molybdenum and vanadium have same crystal structure, same crystalline symmetry, so it's completely soluble. So you can have wide range of compositions. And also, it so happens that MOBSI alloys has been done experimentally. So if you want to test a method, you should always have an experimental test nearby. But for a reason for using aluminium is that aluminium is a good oxidation resistant element, and it's a very good thing to have a good oxidation resistant alloy when you're operating at high temperatures. So, but aluminium is not as soluble as vanadium, so you have to look at the phase diagram of MOLSI. And you can see the T1 phase is only existent up to 30% of aluminium substitution at 1600 Celsius. And our calculations, we went to 2000 Celsius. So to give a comparison, so this is the experimental study I introduced earlier, that they found the thermal expansion of A and C directions against the composition of vanadium. And the direct method from AIMD, if at least for C direction, compares relatively well, but we see a shift in the A direction. But it's still, the trend is the same, and also some experiments done actually came close to our simulated values than the other ones. So in theory, this direct method works for alloying systems and for molybdenum, silicon, aluminium. But here the anisotropy is minimized but not zero. You can't make a zero anisotropy with vanadium alloy, except for aluminium case, the thermal expansion of A and thermal expansion of C intersects at the middle. So in this percentage, you get an alloy with zero thermal anisotropic, zero thermal expansion anisotropy. So we predict that at this composition, you'll get a much better alloy with zero anisotropy. So to summarize this ab initio MD study, we proposed a method that successfully captured the temperature-dependent mechanical properties for intermetallics. And the comparison with experimental results are very good. And in theory, this method should be extendable to other material as well, and hopefully to cement. And because in cement, why these two studies was important is that cement is not zero temperature material. Its application could be high temperature, and also it is inherently a solid solution. So this kind of studies should be very important to cements as well. And also the alloying done using AIMD proved that aluminium is a better alloy as opposed to vanadium. Now to give a roadmap to building a realistic CSH model, this is my hypothesis that we already have Richardson models for CSH1 type of cement. Then a similar argument can be made, and we can build CSH2 type of models. But what we really want is an amorphous model. So to build an amorphous model, we could use these two models as seed models and use ab initio molecular dynamic techniques to build an amorphous CSH model. And hopefully after that, with further studies using AIMD and MC methods, we might be able to get close to what's Jennings' EM2 model. Why is this possible? Well, if you do a rough estimation, Jennings' model is in the order of 4 nanometers. With considering the correct density, it will come out to be about 3,000 atoms, which is still doable with molecular dynamics. So with that, these are the published and some of the work I'm working on. And thank you. I'd like to thank Dr. Ching for all the help and encouragement over the years, Dr. Misra, Dr. Rulis, and Dr. Sakija for their collaborations, Dr. Murochik and Dr. Lee to being in my committee. And I have to acknowledge Dr. Ariel, Jay, Nazir, and Ben for their help over the years, and ESG and CPG group members and the faculty of UMKC Physics Department. Thank you.
Okay, so we will start the questioning, and we will start start with the committee members. So let us start with Professor Misra from KU.
Yes, sir.
All right, so maybe go back one slide. Yeah.
One?
This one, no,
Yeah.
no, the one, this one.
Yeah.
Okay. So you said you want to obtain a model, right?
Yes.
Jennings.
Yeah.
What will you do with that model?
Well, as close as we could come. Jennings model is the only thing that says we are at least within the reach of a 3,000, 4,000 atom. I mean, it was built to explain some of the experimental studies, but not all, obviously. But, well, Jennings model is not very specific. It's just talking about the size and density of the particle. So if we imagine that we get a good seed models from these, because these are much carefully designed models. So if these are used as seed models, it doesn't matter what model we get at the end, we'll get a good amorphous model to represent CSH at that level, and hopefully CASH as well.
Maybe you want to say you will have multiple such models.
Oh yes, I mean it's granted, you're not gonna get away with one model for cement.
Or maybe,
Oh, well, I could follow up on that. So once you have the model, you would be doing what with it?
Well, first we would try to optimize cement, because right now, the only ways of optimizing the real cement is by trial and error and doing mixing. So it's basic alchemy right now. So if you have knowledge at the fundamental level, you could much more easily optimize these properties. And cement is not just for walls. It's used in underwater oil rigs and in various different environments. So everybody wants a model to play with.
So what's your suggestion? Let's say, so cement often that one of the main cause of troubles is that by the water.
Mm-hmm.
So some of your analysis actually consider this water content.
Mm-hmm.
So let's say when your cement is under fully saturated condition,
Mm-hmm.
okay? So then what's your suggestion based on your analysis? What kind of model will work better, or how you can set the ratio of the
Right now, well, it suggests that that hydrogen bonds do play a major role,
Yeah.
but exactly what role is very difficult to suggest. I mean, figure out, because those crystals are
Yeah.
very unique, and especially suolite, it's not synthesized and only found in very few areas in the world. And how to get that kind of hydrogen bonding network is it's very hard to guess. But the general trend is more water you have, the lesser mechanical property you will get.
So what's your suggestion, let's say, if someone, your client asks you that question?
You first have to build a model, then you can play with it, and then I can answer that.
That's the kind of question you get when you a PhD in
Yes.
in the cement industry.
I was curious, you mentioned that when aluminum substitutes in back there, it goes into the bridging tetrahedral
Yeah.
sites. Just a thing in terms of minerals in general, is that always the case? Or why
Probably not.
Why does aluminum prefer a bridging
well,
tetrahedral rather than another one?
From the review, from the Richardson's review, after analyzing all the CSH1 type cements, they came up with the hypothesis that the bridging would be the most prominent replacement, and not the other tetrahedral. Probably from NMR studies, because you can find the coordination number from that.
I'm just curious why it would prefer that over the other sites. I mean, we can observe that it does.
Yeah.
I'm just wondering what the cause is. I wouldn't think those tetrahedral sites would be that different, but it would have a strong preference.
Would you do total energy calculations? You
As opposed to, no, I did not check up on that.
Yeah,
I did
you
not.
could.
I could.
Conceivably, you could do a
Right,
total energy
conceivably I
calculation
could, right.
of what's the total energy of the
Right.
system with the aluminum substituting in one site versus
Right.
the other site.
Right.
Compare the total energies, relax the system in both cases, then compare the total
Yeah.
energies and see.
This is a very recent study, and we're still working on it. So we didn't have that much time to play around with it, but that is, of course, one of the questions we need to find out. And also the vacant sites that would represent CSH1 better.
So how many of these are just theoretical models, and how many are actual phases that have been observed? Are most of these just a model?
So all of these are models.
All these are just models?
So
Okay.
these two obtained from Richardson models. What he did was he optimized, well, the CSH1 crystal, XRD patterns are very broad.
Yeah.
So nobody up to now really optimized the C over Z ratios and optimized the atomic position, especially in the interlayer. So this study is important because he optimized the atomic positions as well, not just the crystalline crystal pattern.
So I think that the committee members can continue to ask questions
Yes.
until exhausted, and we will open to the general audience.
So I had maybe one other question. So regarding the calculations that you did, you did this total bond order density,
Yes.
and basically what that comes up with is like a single number that
Yeah.
characterizes
Right.
the overall bond strength associated with the crystal. But you mentioned that the crystal, in a lot of the different crystals obviously have some sort of internal structure. They're not isotropic
Yes.
necessarily, and so that there is, a likelihood of differences in different directions.
Yes.
And that there's layered structures, and so, two crystals may produce the same total bond order density, but have very different properties internally, just because they have different structures and
Yes.
different sorts of layered structures.
Yes.
Is there a way that you could imagine trying to account for that or bring that factor into your
I
measurements?
think-
What would you try to do to?
I think that's what that's why we went into partial bond order density, to sort of further dissect the total bond order density. Because total bond order density, as I showed earlier,
Right.
did not correlate very well with mechanical properties. But partial bond order density, since it accounts for different species,
Yeah,
gives,
you had the little ovals on each of them. And you
Right.
had the hydrogen, whatever, the hydrogen oxygen one,
Right.
whatever, the bond, the HB one.
right,
That one had the sort of the most
right,
sort of elongated oval.
Right.
But still, it's not like, really, it kind of still reduces down to, instead of one number, you have three numbers, and the number is sort of an overall thing. Is it, could you imagine some other way? So, not that you're going to do it, not that you did, but if you wanted to try to dissect it in a little bit different way, is there some other way that you could try to get to to characterize the mechanical properties of the crystals, to understand isotropy, or sorry,
Well,
anisotropy a
actually,
little
the
bit better?
isotropy, the anisotropy of cement, we didn't include. We have done the study because there's a way. There's a universal anisotropic parameter defined for very inhomogeneous crystals, and we played with this, and we found, although the crystal structure is very different, mechanically cement is not that anisotropic at all.
The bulk cement.
The bulk cement.
Yeah, that's because it's amorphous
No,
mass
no.
in all directions. But
Even the crystals, because we
when you say crystals of, even these crystals?
yeah, or even these crystals.
The ones that people actually
Right.
observe.
So we didn't publish this, but we studied this and found out that the class of crystals we had was not anisotropic at all. Although people, some researchers went on about the anisotropy because it's a layered compound. So anisotropy comes into play, but in reality it doesn't. Not too much.
So there is anisotropy, like apparent, but in terms of
Mechanics,
the
no.
impact
Yeah.
of that sort of visual anisotropy,
Right.
it's pretty minimal, is what,
Right.
is what you're saying.
Yes.
Okay.
Yeah, these things look structurally anisotropic, but when you look at their mechanical properties, the degree of anisotropy which is
Very minimal.
Very small.
comes out
Okay.
is small compared to many other crystals.
Do you have an explanation for that?
Just happened. It just happened. Or
Very difficult to say.
Yeah.
questions from the committee members?
The only explanation I can give is that the hydrogen bonding network in the interlayer is much stronger than what we've seen in any other material. And we saw in some cases where you have covalent connections between the interlayer as opposed to not. The hydrogen bond steps in and increases to bridge that gap. We talked about it in the first paper. So there's a lot to be learned about hydrogen bonding chemistry in the interlayer region of CSH crystals.
Okay. I had another question, if I can butt in here. Number 35, slide 35. So this I think was in your MOSIB work.
Yes.
Yeah, so this is some person's prediction. On the right-hand side, you have the MOSIB T2 phase, and you got your work and their work.
Yes.
And in some of those, the alignment is pretty good, and in a couple of them, it's like almost opposite. Like the C12 is like.
Yes, the shear constants was not that good.
The shear constant was very, yeah. Well, I mean, so that was experimental work. Ito et al.
Right.
That was
Ito's work is the red dots.
And that's sort of experimental observations
right.
of the shear term for this crystal. But then the other ones, like the C66 is not too bad, it just shifted a bit,
Right.
and then the C33 slopes off a little bit, but the trend is right. C11 is, of course, beautiful.
Yeah. And also you had to factor in the difficulty of full elastic tensor measurement of
Right.
crystal.
Right, yeah, so. I just didn't get a good look at that one when you went through it. So I mean, the shear term is often kind of difficult to obtain in terms, like you calculate it, right, and people measure it, but there's often always a mismatch between those two. I mean, do you have any sort of sense as to why that's the case? What's the sort of like a systematic cause for error between experiment and theory in the
Well,
shear
it could
term?
be both. I would say it's both. I would
Yeah,
say
so somehow they're disagreeing, but like,
Right.
is there, what is the underlying, is there some sort of known failure that is just really hard to deal with, or is the
No.
failure unknown and nobody's figured out why yet? What's your
I
take
have
on this
not-
story?
I have not seen anybody reported any known failures in terms of the simulation. The only thing that I could think is, well, partly experimental. It's very difficult to measure. That's
The
documented.
C12 phase.
Right,
term?
the
Okay.
shear. And also ab initio molecular dynamics, I mean, there's a lot of details going into ab initio molecular dynamics. We might not get the angles correct too much. That could be why the principal elastic tensors are better than the shear elastic tensors. After all, we are simulating a smaller cell with smaller number of atoms.
They're not really too sure. Okay. That's an interesting issue. And you mentioned, I didn't quite catch it, on like slide 13, you mentioned that C/S ratio was hard to measure in the cement?
No,
Something like that?
it's easy to
I
measure.
was going to say, it ought to be really, really easy.
It's very
to
easy to
right?
measure, that's why people use it, but it's not very useful.
Yeah, can you go to slide 13? Yeah.
Yeah.
So here's the C/S ratio, very easy to measure.
Very easy to measure.
Right. It has the bond order density, obviously, and you can't measure that. I mean, it has to be calculated. The trend, though, for the C/S is like, you know, an inverse trend, right? So even though it's doesn't follow exactly, it's an inverse trend with all those, at least to my eye, those mechanical properties align pretty well with the C/S ratio if you imagine it as an inverse relationship.
For four crystals, you can almost say anything. I mean, these two parameters would be, that's why we didn't really say anything about it in the study. But when you go to 20 crystals, it fails horribly.
It does, yeah. So is that, my next question was, in terms of like the actual cement, is the C/S ratio a good indicator of
No.
Like, so people measure it, but then they have like no real utility
Yeah.
for it,
Yeah.
and
Because I mean, you make
it
cement,
doesn't
you have
it doesn't correlate.
X
well.
amount of calcium oxide and X amount of silicon dioxide. It's lime silica mixture,
Yeah.
so it's easy to think about. But when you're trying to characterize it, the hydration process of cement
Really
is
complicated.
really complicated,
Yeah.
and it goes for years and years. So what you start with is not what you end up with, even the COS ratio.
Exhaust the questions from the committee members.
For now, yeah, I think I'm done.
So I add one last comment, and it's only comment and not a question. So the elastic constant you actually obtain mechanical properties you obtain actually from two ways, ab initio MD and also stress and strain.
Yeah.
But the CID obtained from stress-strain relation is all within the linear elastic
Linear
field,
field, right,
which has
right.
its own limitations. And so the future is in the really very accurate, large-scale simulations,
Right.
which would actually include a nonlinear effect.
Yes.
So this is only a comment.
Yeah.
So, okay, this is open for the other people to ask even tougher questions.
I don't know, this is a difficult question, but following up on how long the hydration process takes, and how, I guess, hydrogen bonding, I imagine, is an important part of structural properties. And I'm sort of imagining, well, concrete may age over a period of time, and maybe it does or doesn't deteriorate. I guess that has something to do maybe with the hydration process and why
Yeah.
it maintains structural properties.
Yeah, hydration process, because when you make cement, there's unreacted clinker, and the other elements like gravel might have, and also you have structural water stuck in the interlayer always trying to react. So the studies have gone for 25 years, and they still find reactions in cement. So it's a continuous process. It drops down exponentially after 30 days. But 3 years, the studies is going on. That's why it's been studied for more than a century.
That's kind of interesting.
Any?
Yes.
Yeah.
I'll introduce myself since nobody here knows me. I'm Dr. Kevin Armendariz. I work at Ashgrove Cement. I got the invitation through my director, Greg Barger. Anyways, my question relates to the models that you were talking about and kind of your plan for maybe getting your CSH2 model and the amorphous model, and how that would
Right.
come together to help you make a predictive model for mixed designs, and that can be very helpful for us because we have people dedicated to doing just that work to get the exact properties that we want for our finished cement. So my question comes down to, like, it looks like in the models that you have, and I'm not familiar with actually the modeling portion of this, you've preset the chemical constituents you have and basically just let the simulation run. Is there anything that you can do to see how, I assume it's a fairly uniform mix whenever you start that simulation, or is it
Well, the thing
so
is
much
with
freedom for stuff to move around or be different in multiple areas of the simulation?
So if you vary n, it's a very difficult simulation to begin with. You can do, there are multicolor techniques to do it, but at least in ab initio studies, it's you have to keep your n constant during the simulation. The solution to that is have as many models as possible. You set your composition early on, then you do your simulation. That's why, for example, Richardson model, you can't get away with just one model. You have to give a class of models or a rule to say this class is possible.
Okay, that makes sense. And kind of what I was thinking was, if you had either multiple models, like you said, or a model that could incorporate, you have a tremendous mixture of different chemicals that go in. So you have your C3S, your C2S, your C4A. They're all being hydrated together. Like, can you look at hydration with a model like this, or is that be just too far beyond the scope of what these?
Well, there are studies done to model hydration, at least gas phase calculations, but I wouldn't say it's very effective right now. There are other Monte Carlo methods that uses, you fix, you connect that to maybe a water bath or something else, then your N is different, and until your chemical potential in the simulation cell is optimized. There are simulations like that too, but those haven't really panned out any real model so far.
Thank you.
Any questions?
Ted? Yes.
I think you told us that this is a highly popular model.
Yes.
What is the reason behind this?
Oh, when I was explaining the Richardson models, I said that CSH1 and CSH2, one is coming from topomorite family of crystals, and two is coming from genite family of crystals. Actually, the main reason is the more broadest peak of normal cement relates to this this interlayer distance somehow. That's how people picked up on that in the early 50s and 60s, that these might be prime candidates for cement models.
So there is some mechanical property, something different, or this is a highly usable mechanical property?
No, it's just the fact that you find that broad peak for that interlayer distance in XRD. And as the Jennings CM2 model, it still have freedom to have porosity in the cement particle. So that the reason why we cannot really say that it's totally amorphous is because you still find some structure in XRD patterns in cement.
You were talking about having two different models, one for the CSH1 versus 2, and those there seems to be a cutoff, you said, about